Now I'm going to talk about another very important imaging technique, that is MRI. It's a short form for magnetic resonance imaging. As the name indicates, it uses magnetic property of the tissue and the magnetic field to produce the image. It's a relatively young technique compared to ultrasound. So the MRI imaging techniques was developed in 1970s, and the first unit in Norway is 1986. So before we continue the session, please keep these questions in mind. What's the difference between MRI and ultrasound? And what's the advantage of MRI? If you cut the MRI open, it will look like this. It consists of a big magnet, which is in yellow here, and a radio frequency coil here used to send in pulse and pick up a signal. It's similar as a transducer in ultrasound. MRI managed to take a whole body images, which ultrasound can only take local images. The biggest part of the MRI machine is the strong magnet. Actually, as you know, you are inside the Earth magnetic field all the time, but you don't feel it because it's too weak. However, compass can feel it. The strong magnet you can find in daily life is a junkyard, which is powerful enough to lift a car, but it's still weaker than the weakest MR machine for normal patient use. So here is junkyard magnet, which in magnetic field strength we describe in Tesla unit. So this is 1 Tesla, and the MR scanner is 1.5 Tesla, and now the more common one is 3 Tesla. And for small animal imaging, we are around this scale, about 10 Tesla. We have to use much stronger magnet for small animal imaging because it requires much better resolution as the organ of the mice is much smaller than humans. Yes, here is a small test about magnetism. If you're interested, you can pause and think a while. Yeah, these are the answers. So it's a gravity sticks you to the floor. And it is the magnet to turn electricity into motion. And the Earth magnetic field is much weaker than fridge magnet. And if you cut a magnet in half, you will get 2 magnets. Instead of the magnetic property disappears. One of the property of magnet it will change the position or change the direction in other stronger magnetic field. As shown here, if you put a magnet closer to the compass will point to the direction to the external magnetic field. So actually, the water molecules, which our human is composed of more than 60% of water, they behave like a small compass. Yeah. And when they are inside the strong magnet, as lying in the MR machine, these small compass will align themselves in the magnetic field and create a strong magnetism. And then the RF coil will send in the pulse, and the water molecule will absorb the energy from it, and then when the pulse stopped, it will emit the signal to let the IF coil to receive the signal. And used for reconstruction of the image. The most common application of MRI actually is neurological imaging. MRI can study the brain anatomy to see what the brain looks like, and a much advanced or recent application is to study the function in the brain, the different region of the brain. So here is a brain anatomical MRI image of a patient with a brain tumor. Here is the tumor. When this patient was asked to perform certain tasks like speech, finger tap, and listening, different region lights up. So this is the functional MRI study. In our lab, we are mostly doing preclinical cardiac imaging. We use the same or similar techniques and protocols as human MRI scanning. But as I mentioned, the organs from mice is much smaller than humans. This is dogs. Humans are even bigger. So it requires much stronger magnet and to get a much better resolution. And also the heart beats much faster. It's 10 times faster than humans' heartbeat. And also the mice and the rats will not lie still in the magnet by themselves. They need anesthesia. And they also cannot hold the breath to reduce the movement. And this is the scanner in our lab. We are scanning the heart functions and the structure. The most common or essential protocol of cardiac imaging is called cine. The name comes from the word cinema. Compared to the low-resolution ultrasound, MRI offers much clearer images and at whatever view plane. Conventionally, we choose 4 chamber. At this one, you can see all 4 chamber of the heart. Or this is cut middle ventricular. We call the short axis view. So this is the left ventricle and this is right ventricle. So this is the heart cycle. From cine images, you can not only get the morphology like heart mass, wall thickness, blood volume, you may also get the functions. The most important one is called ejection fraction, which now is the gold standard for defining whether patient has heart failure or not. Now, what is ejection fraction? It is the amount of the blood pumped out compared to the original blood in the chamber at end-diastole. It measures how much blood is pumped out at each heartbeat. So if the value is between 50 to 70%, it's normal. If between 41 to 49 pumped out, it is reduced at the borderline. And if under 40%, it is called as reduced ejection fraction. And this left ventricular ejection fraction is the current benchmark in heart failure. So here has 2 hearts. Let's take a look. Left is a normal heart. At end systole, the blood volume is 50 milliliter. and under downslope 120 milliliters. And on the right, it's a bigger heart. It's the same volume at under systole and under downslope as a normal heart. So they get the same ejection fraction. But obviously the right heart is not normal. It has a pathology called hypertrophy, and which will eventually lead to heart failure as well. So this is a type of heart failure with a normal or preserved ejection fraction, which of greater than or equal to 50%. Then researchers try to find another marker to better describe heart failure. That is called global longitudinal strain. How we define it? It is from endodiastole to endosystole. The heart is shrinked at longitudinal direction, and the distance it shrinks compared to the original length, then this is called strain. That is called global longitudinal strain. It measures how well myocardium contracts. As we can see here, with the ejection fraction from very low to quite normal, over 50%, the probability of death doesn't change much. But if the strain from very high to very low, the probability of death increases. So it shows global longitudinal strain is a better indicator to predict outcome. MRI is also superior to detect the microstructure of myocardium. This is the heart with this dark region is the infarct region and some focal fibrosis. And the infarct region here can be lightened up with the help of contrast agent. And now it's the gold standard to measure infarct size in vivo now. If more diffuse the fibrosis, like from aging or from hypertrophy, then MRI also can be measured by a technique called extracellular volume fraction. I will not go to detail at this course. MRI can also detect the fiber orientation. Here, as you know, the heart is not a piece of homogeneous tissue, so it has special orientation, and these special patterns, they perform different tasks: compression and shortening. And the MRI can use to measure the fiber structures. Here is a infarct rat heart at 3 days, 10 days, and 6 weeks. So this region is the region with the infarction and lost the organized fiber orientation. As we have seen, MRI is a powerful and versatile imaging technique. But there are some safety issues needed to be considered. The most important thing is that the magnet is superconducting, which doesn't need power, and it's emerging liquid helium at minus 273 degrees. So it's always on and very strong, stronger than the magnet which can lift a car. So be careful. So in the cases, some ferromatic material is strongly forbidden, like accident examples. At last, let's take a look at both ultrasound and the MRI images of the heart. These show the same views at the same plane. And as you can see, show clearly the advantages of MRI. It has superior soft tissue contrast and the resolution. So as a comparison, how they produce images. Ultrasound use sound waves, and the magnetic resonance use magnetic property of tissue. The spatial resolution actually ultrasound is much better, and it takes a much shorter time to examine, and the magnetic resonance take usually much longer time. So ultrasound is usually real time, it's cheap compared to magnetic resonance. Very expensive, but it has a much better tissue contrast. So the disadvantage of ultrasound is low image contrast. And you cannot see any plane. You also need to assume some geometric to estimate heart volume. That's all, and thank you for your attention.